Welcome to Monochemistry. In this lesson, we're going to learn about the energy and the speed of gases. And we're going to learn more specifically about how the energy and the speed of gases are related. First of all, I'm going to introduce these two gentlemen here. These are the two physicists who came up with most of the theory we're going to talk about today. And this man here is a physicist named Maxwell, and this man he's a Scottish physicist, and this man here is a man named Boltzmann, who actually has his own constant, which we'll learn about later on in this course, and he's a German physicist. Now, you might be thinking, why are we learning about physicists? I thought this was chemistry. I don't really want to take physics. Well, whether you like it or not, chemistry and physics are intertwined, intricately intertwined. So you sometimes find out a lot about physics when you learn about chemistry, or you find out a lot about chemistry when you learn about physics. In this case, we're learning about energy and speed, which are both physical properties, and so they're physics in nature. But they have to do with gases, so that's chemistry. Anything that has to do with matter is chemistry, and that's how they fit together. The first group of experiments that these gentlemen did revolved around the effect of temperature on the speed of gas particles. Okay, so here in this graph here, we have on the y-axis the number of molecules, and on the x-axis we have the speed. And what we're assuming here is that the temperature is going up. So as the temperature increases, and we can assume that the gas in this, forget about this key here, we can assume that the gas here is the same gas but at different temperatures. Okay, so this number of molecules here represented by this blue line would be at the lowest temperature, and then if we increase the temperature, this is what would happen, and as we continue to increase the temperature, this is what would happen. But it's the same gas for all three of these. Okay, so what is the effect of temperature on the speed of a gas? If you look at this particular graph, what you see is as the temperature increases, the speed of the molecules of gas become faster. Makes sense, right? So the speed of the gas is dependent on the temperature. They're proportional to one another. Let's continue. Another experiment they investigated was the effect of the mass on the speed of gas particles. Now, if you take a look at this graph here, you'll see that you have four gases. Note, you have helium, neon, argon, and xenon, the noble gases. Now, if you look on your periodic tables, what you'll find is that helium is the lightest of the gases, and xenon is the heaviest. So what we find here is that the relationship between the mass and the speed of the gas particles is as follows. The lighter the particle is, the faster it travels at a given temperature. The heavier the particle is, the slower it travels at a given temperature. So let's pretend this is 25 degrees Celsius. Doesn't matter, 298 Kelvin. So that's it, right? Does that make sense? Does it make sense that something heavier would have a harder time getting around than something lighter? Something lighter would be easier to move around. I think it does. So what can we take away from these two observations? Doesn't really seem like rocket science, does it? Well, some of the math that these guys did was a little... So here's what we have. We have kinetic energy and root mean square speed. Okay, so what we know now is that kinetic energy, the energy of the gas particles, is equal to 1/2 the mass, that's the mass, 1/2 the mass, times the velocity, that's meant to be, it's it's meant to be velocity. It's a u, but it's velocity. Okay, so 1/2, and actually it's not velocity, it's speed. My apologies. Okay, so 1/2 the mass times the speed. Okay, and those of you that are familiar with physics know that the difference between velocity and speed is simply that velocity is a vector quantity, which means it has a direction as well. This direction does not matter in this particular equation, so it's just the speed. Okay? Alright, so kinetic energy is equal to 1/2 the mass times the speed squared. And as we've said before, it doesn't matter what type of gas particles we're talking about. The kinetic energy of two gases at the same temperature will be identical. Now how can that be? If they're not going to be moving at the same speed and they don't have the same mass, how can this be true? Well, if you multiply these two things together, they end up averaging out. Okay, so if something has a really big mass, its speed is going to be really low. If something has a really small mass, its speed is going to be really high. And so therefore, when you multiply them together, they end up averaging out or equaling about the same. So the kinetic energy for any two gases at the same temperature, any number of gases at the same temperature, is always going to be the same. Okay? All right. This quantity here, the second equation, is called the root mean square speed. Okay, so it's written like this, or in your textbook it also is written URMS, root mean square speed. Root mean square speed. Okay, and it is equal to the square root, that's why it's called the root mean square speed. It's equal to the square root of 3r. We've talked about r before, but this is a different version of it. We'll talk about that in a second. T is temperature, divided by molar mass. Okay, so the velocity of the substance is related to both the temperature and the molar mass of the substance. The constant that you use in this case is 8.314 joules per Kelvin mole. Okay, and the units for kinetic energy will be joules or kilojoules, depending. And the units for root mean square will be meters per second. That's what you'll end up with. And it doesn't really matter. I will go over in class what these units, how they work and what they all mean. But those are the units of these things. So when you calculate a kinetic energy, you should have joules, and when you calculate a root mean square, you should have meters per second. Okay, so 8.314 joules per Kelvin mole is the value of R in these questions. Okay, and that in a nutshell is both the kinetic energy equation and the root mean square speed equation and how they're related. Obviously you need this value to calculate kinetic energy, and if you take the square root of that value, you get your root mean square speed. Okay, so they're related to one another. Make sure you bring your questions to class. These are the sources of the pictures that were in this video.